Usually when we want to study something, we will have a set that contains all objects of interest. For example, we have R. This is the set of all real numbers. This is the set of all real numbers. We have C. This is the set of all complex numbers. The set of all complex numbers. Yeah, so when we study vectors, we want to do the same thing as well. I would like to look at the set of all vectors. But to do that, I need to first say what I mean by vectors then. So a vector is anything that has all of these properties that we have down here. So if I add a vector by a zero vector, then I should get the same vector back. If I add a vector to the negation of itself, then I should get zero vector. And vectors are commutative. If I add u and v, that's the same as adding v and u. And they are associative. If I have u plus v plus w, it doesn't matter which pair I do the addition first. If I multiply 1 to v, so I get the same vector v out. If I multiply a to bv, that's the same as ab and then times v. Vectors are distributive. If I multiply a to u plus v, that's the same as au plus av. And if I multiply a plus b to vector v, that's the same as av plus bv as well. So this would apply to anything, not just the vector in the usual sense as well. As long as whatever I have satisfy all these properties, then I'm gonna call those a vectors. Now then, what do I mean by all vectors then? We knew that when we have the set of all real numbers R here, this is already all the real number that is. It's gonna be all those things on the number line. And this C here, this is the set of all complex numbers, so it's all the complex number on the complex plane. But how do I make sure that whenever I make a set of vectors, they are already all the vector that is? Well, the way that I can guarantee that is to look at the linear combination. If my set of vectors is closed under linear combination, then I can be sure that that set is already going to contain all the vectors that I want. And whenever my set of vectors has all these properties, I'm gonna call them a vector space. I'm gonna use letter V for that. So this V stands for the vector space. So basically, a vector space is just a set of vectors. They are objects that has all these properties and they already have all the vectors, so that means they are closed under linear combination. So if we look at the example down here, the set of usual vectors in 2 dimensions, in 3 dimensions, or in any dimension in the usual sense in the coordinate system. This is for an example of a vector space. Or I can kind of think of complex number a plus bi as a vector as well. I can just write this as just a vector ab. And then my vector AB here would have all the properties that I have up here and they are closed under linear combination. Or if I have all polynomials ax squared plus bx plus c, I can just think of this as a vector ABC. And it would still have all the properties that I have up here. Or I can kind of apply what we have up there and think of 2 by 2 matrix. So I'm gonna have a matrix. Although I kind of have 4 elements here, but I can just think of this as just some fat vector, basically. I can just think of this as just some fat vector. Yeah, because it has all the properties that I have up here. So once again, in the sense, the vector space doesn't have to be just a set of vectors. Anything that has all these properties, I can think of them as a vector. And then I can also think of the set of all polynomials and the set of all functions as just an abstract vector as well. Because, whenever I have a polynomial, then I can think of a linear combination of polynomial as something like this. So I'm gonna have a1 times p1 plus a2 times another polynomial p2, and so on to an times another polynomial pn. Or this p1, p2 to pn can be a function from R to R as well. So whenever I have something like this, if my p are polynomial, then the outcome that I have here are still going to be a polynomial. So the set of all polynomials, this is closed under linear combination, and that's the same with the set of all functions as well. if all my p's here, if these are functions from R to R, then what I have down here is also going to be a function from R to R. So in a way, the set of all polynomials and the set of all functions, these are a vector space, although they are not vectors in the usual sense, but I can think of polynomials and functions here as just some vectors, basically.